49. First a note. The people who marked this as a red problem were stupid people. Do not be intimidated by it. It is actually a fairly simple problem. We can solve it using a right triangle. Here's how we'll do it. Let's say, so first of all, these two springs are in parallel, and each have a constant k. So for simplicity, we'll be modeling them as a single spring with constant 2k and length L. When stretched, according to the Pythagorean theorem, this spring has length root L squared plus x squared. That means distance stretched at the distance root L squared plus x squared minus L. Well, note that we don't have any units here, as they'll get squared along with the distance and put in the square root and get. What I'm saying that they will get squared along with these terms, taken out of the square root, and you'll wind up with the same unit. For instance, if it's meters, this is a quantity of meters. There's meters, it can be in feet, it can be in parsecs if you want, but that's unimportant. So, by this expression, we can say that the force exerted on it, it's two strings working together, so we're modeling it as one string with constant 2k, remember? But the thing is, this force is that way, and we want the component that's going that way. So, we multiply by the cosine of this angle, theta. Now, from looking at this right triangle, we can see that the cosine of the angle theta is equal to x over root L squared plus x squared. So the force we want, the force in the x direction, is which is just let's note that there's no force in the other direction for a moment. Why is this? The reason why is because the two springs that are working together in the case of the direction we are solving for are working directly opposite each other in the other direction. So, because they have the same spring constant and are stretched the same length, it follows that, and are therefore at the same angle and directing the same proportion of their force in that direction, L over root L squared plus x squared, for the record. It follows that the forces in opposite directions are the same, and therefore they cancel out, so we can ignore them. Oh, yeah, and we need to attach an I onto the end of this one, because these are vectors. Because you already figured out what the displacement was, figuring out what the kinetic energy is will be fairly easy. As I mentioned, there are two strings working together, hence the 2k. So delta x equals so it follows that No. Oh, no, wait. Yes, yes, yes. It says in the third chart to draw a graph and identify all equilibrium points. There's only one equilibrium point at 0, and that's because the force is 0 at 0. The rest of the graph looks approximately like a quadratic graph, like so. We'll check the graph in the back of the textbook, and then we will be done.